Okay, thank you very much for joining today. Today we're gonna dive into the third chapter from the modeling section, which is model building. The previous chapter, Alan, you gave us a good intro on what models were. So today I will dive into this section, model building. So um, and Hadley takes two ways to discuss about building models. The first one and the second one. The first one is to think about modeling by partitioning your data into pattern and residuals. So when you want to do modeling, the first step you want to do is to find patterns given data sets and you want to do modeling. The first task you want to do is find patterns. And how are you going to find patterns? Use visualizations. After you find the pattern with visualization, then use models to make that patterns concrete. So when you find a pattern using visualization with the data, now you have some insight what the model is. Okay, it is linear, there is this kind of relationship. Then the next step is to use the model to fit the data to make that visualization you had more concrete. And you repeat the process, but now you replace the old response variable now with the residuals from the model so that you see the data, how it looks. So this is the first approach. And this approach is easier to apply to new domain because you have visualization and you have models you can tweak and do another model. But for very large complex data set, as I said, this is a lot of work because you have many steps. You do visualization, you pick the model, and also you use the residual. But the second alternative, which is most widely used, is using machine learning. And the machine learning has some kind of powerful predictive capability, which tends to draw more attention currently. But the cons of this machine learning, they are black box, especially with recent neural networks approach. You just have give a models data and just it makes prediction. So there is issue of explainability and interpretability issue with this kind of approach of machine learning. So as Hadley said, you can combine the two approach in some cases. Yeah, if your task is not that complex and you need to do some kind of visualization at first to understand your data, so you can follow the first approach. But for complicated tasks and you need somehow automation. For instance, you have data coming, streaming data. You don't wait to do visualization and see the patterns. In such case, you automatically build a predictive model that as the data comes in, it will keep doing the prediction iteratively. So this is a little bit of two approach you can do modeling. So I really like this quote where the Hadley made in the book, because I'm currently at this stage where I'm trying to do a model for long, and I'm trying to tweak it to add some stuff to make it better. But when I just read it, I say, okay, I dump this work. I no longer tweak. Let's move forward. So this, what Hadley is trying to say is that as you are doing modeling, don't expect your models to be somehow because when we're talking about modeling, we are talking about the predictions in some sense. So don't think always that you need perfect prediction, you need perfect answer. So just try as much as possible to see that you have some reasonable prediction capability and move on. If you don't have that, you can redo that again. So this is the basic introduction of the chapter about the modeling. And I think the chapter may take us to presentation, Alan. I will take us through the half part of the chapter, and next week we can do the second part. Right. So let's look at how we can do modeling using the first approach. So as we said, the first approach involves 3 steps. We do visualization, we fit the model, and we replace the variable response variable with our residuals. So let's get an example and do the modeling. All right. So this is the data set that we're going to use. The use case is why are low quality diamonds more expensive. So we're going to use a data set for the diamonds, and we will see that there is some kind of intuition in the data set in which low quality diamonds, which are poor cut and bad colors and inferior clarity, which they don't have good clarity, they have higher prices. Now, how can we model this data set to have a good prediction in terms of the price and some part of the parameters such as cut, bad colors, and cut clarity? So let's look at this and see how the data looks like. So this is the data set, and we have different variables that indicate the low quality of the diamond, and this we have price along here. Let's look at the box plot to see what these are telling us. So if we look at the first one here, we can see that it ranges how good the diamond is increasing in this way, and this is the price. As we can see here, the price of good, very good, we can see the poor, the fair one also has such kind of equivalent prices. Can you see that with the good and the ideal and premium? So it is looking also, the fair is also, the price is so expensive or somehow equal with the ideal and premium, which are more or less somehow not true. We can also look at this one, the color. So the bad color is J, the good color is the color is decreasing in quality. So this is the best color, this is the bad color. So look at the prices, and we can see that the J with bad color, you can see the price is higher, right? And you look at this one, the one with good color, look at the price. We have some price, which, you know what I mean? So you can see also the median price, you can see the median price of this was is even larger. Is none of these other diamonds, which is these colors, which are good, have even the median price comparable to the other ones. So we can see that this is somehow tricky. And the last but not the least, if we look at this one, the clarity. So this one also, we can see that the clarity decreases. So this is the decreasing clarity. This is the worst clarity. So this is the one that is not well clear. And we can see that the price, okay, it's going in this way. So this is the I1, is it I, is the worst, is the one with the worst clarity. So, and this one is, so you can see that the one with high clarity, I mean, perfect, the good one, look at the price, low price. But this one, the worst clarity, look at its price. It doesn't have, you know what I mean? It doesn't have, look at the price, and look at this one with good, look at its price with higher price. So this is really a problem if we want to do modeling. So what's the problem now? There is an important compounding variable here, which actually affects this kind of visualization. So which is the weight of the current diamond. So the weight of the diamond is the single most important factor which determines the price of a diamond. And the lower quality diamond tend to be larger. So this is the problem. The lower quality diamonds tend to have tend to be large, and therefore this trying to do this visualization tries to tell us that okay, they have give us a wrong interpretation. So in this way, if we do modeling using machine learning in some sense without trying to do the first approach, which it takes 3 steps: do visualization, see your data, understand it. Next step, do the modeling, then do the last part. But if you do the machine learning approach, which actually just do the prediction, it may in some sense give you a wrong result in which we have the confounding variable, which will negatively affect the predictive power. So how can I model this data to predict price based on the current? How can we model this data to predict price based on the current size? Right. So this is the problem. So we want to do prediction of the price based on the current size. So as we have said, we are going to do the first approach, and the first approach, we have three things: visualization, modeling, repeat the process. So let's look at the first one, and we have seen some have a look at the also this box plot of the data at the beginning. So when we want to do the modeling, the first one is this. So we can see here we have the correct. This is our data set diamond, and this is the correct, and this is the price. So when you do the visualizations here, we can see that, of course, here there is some kind of relationship between the correct and price. But however, as we can see, we have some kind of outliers, as you can see. So the more we have the correct, the size here, and the more price increases. So this is visualized. So having a look at this, without doing first prediction, you can try to see, all right, I have outliers. Now, for me to have a good prediction, I need to remove these outliers, because outliers, they have negative effect on our prediction capability. So when you do visualization, the first step, you will have a sense of how to structure the data, how to, in some way, transform the data. So even in machine learning, we don't just give the model the data to do prediction. We do some visualization so that we understand the data before we give it. So this also applies to that one. So having looked at this one, we need to take steps in which we can cut this size of the data, where we have the data which is looking somehow outlier. We need to remove it. After we remove it, then we can do some sort. So let us make relationship between the current and price more pronounced. So how can we make this relationship more pronounced? If we remove this part, we cut this one here. If you cut this one and use the data only here, we can actually see that the relationship is more pronounced. And also, because this is a linear relationship, we can take the log of this variable of the price and current. And the log transformation makes linear pattern easier to find the relationship. So if we can see here, right, okay. Okay, so here we subset our data diamond to include only those with less than this size, as we can see, and we log transform our variable, the predictor and the response variable. So we can see here, after doing this log transform, we can see that this is our relationship, which is linear. And of course, we can see that confirmed here, there is a relationship between the price and the correct size. So, but before we do that, after we do log transform, and if we do not remove this size, this one, which is outlier, let's see what will happen. So if we look at this one here, so this one, we do the log transform, but look at it here. We use, okay, this is the Diamond 2 data set. This one, right, okay. This is the Diamond 2, and this we put the correct, those ones that are not log transform. Look at it the way it does, but we put, okay, log transform. I want to put log transform price here. Oh, okay. Now the price, L carat, L price. Okay. L price, L carat, okay. Right. I'm still seeing this relationship with this data. Didn't I caught this one?
Yeah, I don't know why.
Okay. I'm using
data.
Yeah, I'm using diamond one. Just the normal diamond. Okay, I have S. Diamond two, this. Yeah. So here, if you look at it here, I didn't remove the those points, and you can see it's still. So the important point here is to we remove those data that are greater from here, and we also use this variable, we log transform this. So these are the important point we want to mention here, is that we want to transform the data from the original shape. The first step is to subset the data to include only these ones and remove the outliers, and also to use the log transform. And why do we do the log transform? Use the log transform allow our data, allow our relationship to be easy identifiable. As we can see here, we can easily identify that this is a linear relationship. Now, we have done the visualization part. Now let's look at the modeling part. So the first thing at the modeling, you feed the model. So this is the model, we feed the model, and after fitting the model, we do the prediction. Right, so this is it. We that data grid, we put these 6 arrange correct, yeah, and we also mutate, create a variable called log caret, and we also add the prediction. But you can see here, yes.
So Shamsuddin, it's, I don't know, when I was going through this briefly, I was wondering why they're using log2.
Yeah. This is a good question. This is a good question. Uh, yeah. So I thought basically they're supposed to just use log to find the transformation, but I'm not quite sure actually why using log 2. And I just keep my mind, I was trying to even check why using log 2. So yeah, maybe I don't know how someone can answer us. I'm not sure.
Yeah, the base of the log shouldn't matter, because like you can convert from one to the other with like simple arithmetic. So even if you use, I don't know, natural log or log 10, you should see a similar plot with just the numbers changing.
Yeah,
because it's really, it comes to the interpretation of the axis, right?
Yeah,
So,
and 2 kind of makes sense, because you can think about, like, if I double the price, or if I like an increase of 1, like +1, translates to multiplying by 2. So it's a good base. Maybe that's why they've picked it initially.
Okay, yeah, because okay, that's a good one, because I'm used to using 10, and basically it's the same thing. So with 10, you increase by 10 points. So with 2, it's more easier to interpret, I guess.
I don't understand what you mean. What you said? How can you come in again?
Yeah. So when you log transform some number with base 2, let's say, I don't know, well, log 2 of 4 is 2, right? 2 to the power of 2 is 4.
Yeah.
Log 2, or like if you get 3, then that's 8. So if you increase 2 to 3, you're actually doubling the original value. So log 2 of x, right? If you increase that by 1, then x has doubled. So it's useful as a base. And as Alan was saying, 10 is also useful, because then +1 is equivalent to like the original value of x being 10 times its previous value. So to kind of make sense, in that we're used to this idea of like twice the size or twice the price or twice the, I don't know, weight. But you could use any other base and you would get the same shape.
All right. Okay.
It's just different numbers, right?
Yeah. Okay.
Good.
Thank you. Good. So yeah, so we can see here we have data grid. So using data grid, we have our cohort, which within this range, and also we create here in the data frame L Cohort, log transform Cohort, which is basically also using log 2, we take the transformation and we add prediction. And you can see mod diamond, we put the name of the model, and you can see now here, we rename it to be L price, log price, because this model is using the log transformed price. That is why we put here. So we named this one here. So, and finally here, we took the price back to its original shape. So you know in log 2, when we take the 2 power of the log of that stuff, it will give us the original result, right? Does that make sense?
Yeah.
Okay. Yeah. So in logarithm, when we have the base log 2 of x, so when we want to find of x, value of x, so we take the 2 power of the stuff. So that is why here, if we have the L price, which is the prediction, then this one will give us the original prediction. So looking at that one, that is why here we have the Cohort here, and we have this one here, L Cohort, and we have the L price, which we rename to give us this one, and also we have the original price. So we can see here, we have the data grid, we create the grid, and what else? We create the feed the model, we create the grid. What else next is to plot. So we can see here, this is actually the prediction, and this is the actual one. So fitting also the model using the grid and using our transform data and the original price and Cohort, so we can see there is actually a linear relationship between the price and Cohort. Yeah, so this is about the model. So the model shows us that large diamonds are much cheaper than expected. This is probably because no diamond in this data set costs more than 19. So if you look at this one here, this is 20.
I guess we can say logarithmic relationship.
Yeah. So I mean, if you look at this one here, this relationship, no, not this one. Right. What? Okay, 150. Okay, yeah. So this model shows that the large diamonds are much cheaper than expected. This proof because no diamond in this data set cost more than 19. What does this statement mean? I took this statement from the book. I was expecting before that this price was much higher in the previous cases we have seen, the first one, but it's still the same. I mean, it's still the same. I mean, here, okay, let's see the first one. The price is here. Okay, they are still the prices. They are within the range of 20,000. And also here, when we do the modeling, it's just they are below. So what does this statement? So someone can interpret this one. I don't really understand what this means.
So it looks like in this data set, there's an upper limit of the price, which appears to be around $19,000. So this means that if you imagine, if you look at the earlier parts of the curve with lower carat values, you can see that it's sort of growing exponentially and it's sort of widening as well. But as we're going higher and higher in value, because we have this upper sort of cutoff, in essence, we're sort of slicing the top half of our like more expensive diamonds, if that makes sense. Like, so if this $19,000 limit wasn't there, we can imagine that, you know, diamonds of carat 1.5 or greater would actually have gone higher. So our model is kind of biased a little bit because of this upper limit. Does that make sense?
Yeah. So as we see this one, it goes here. The price is limited to here. So even if the Cohort size increases more than 2.5, maybe we have 5, the size will still be linear, right?
Yeah, so basically we're only catching the cheaper of the more expensive diamonds because our data set is limited. So if we didn't have this upper limit, we would probably see many more diamonds above 19,000, 20,000 when the sizes were much bigger.
Yeah, okay, yeah, that makes sense. So so this is the second part of where we do modeling. We have seen the first part where we visualize the data and try to find patterns, and we have seen now how we can fit the model and just fit the model, find the grid, add the predictions, and plot to see also how the model performs. So this is the model plotting of the model and its performance. So the next one is residuals. As we said, in this first approach, we visualize the model, fit the model, and we use residuals. In this case, what we do is we put the residuals at the place of the response variable so that we see how the performance of the our modeling task. So here we're going to use this diamond data set that we subset. Just a reminder, we are going to use this data set that we have we used before, and as I have said here, we're gonna put here. Okay, now we're gonna add residuals here. This is add residuals. As we know, this is how we do it, and this is the models. We already fit this model, and we call this one to be r4ds. So if we have this one here, and when we look at this one here, we can see okay, so let's see this. What's the meaning of this? So let's see. Okay, we have many columns here, so we cannot see them. Right. Okay.
But yeah, definitely it might be in the environment if you just view it instead.
Ah, right. Okay. Why?
No, you can just view it from the console.
Okay.
I think it's capital V, and also you might need to sign it.
Okay, so capital V. Okay.
That works. Okay, now ignore that.
Yeah, so we have this one here, right? So yeah, so we have that, and
sorry, hold on a second. Could you bring that back up again?
Right. Yeah.
I guess we might actually be able to see it in the picture, but
So what is happening is Diamond 2 previously has some properties that we already added. If you look at it here, we have log price, log Cohort, right? And yeah, so now what we added now is log residuals. We already have this one in the previous Diamond 2. We override the previous value of Diamond 2, and now we mutate another value in it and add log residuals. And we already have these variables from the original Diamond dataset. These are the new values columns we added, and this log price is the log of the price. We do that, and this is the log of Cohort we are talking about, and this is the log of residuals that we have just done. So these are the two columns. Yeah.
Okay. So yeah, it's the residues are ranging between from 2 to -2.
You see what?
The residues are ranging from -2 to 2.
No, you have -8 if you look towards the
-9.
Yeah.
No, that's gonna be 0.0 because of the.
Oh, right. Yeah.
Yeah.
I didn't see that.
So, can we continue? Shall we continue?
Yes, please.
Okay. So Right, now we have this and we want to plot this one. And if you remember here, we said here we have the log of the current and the log of residual. So remember here, the first one, what we have is log of the current and the log of price, right? So here we change in the residuals and we can see here what happens. So as we can see these visualizations, this doesn't make any patterns. So this confirms to us that since the residuals plot doesn't have any pattern, it doesn't follow any kind of pattern. So it confirms so the models seems to work. We have residual which are good enough to show us. This is how I understand the residual plot. Does that make sense? Or
yeah, I think you understand it quite fine. I myself, I can't see any patterns I can identify.
Right.
Yeah, there's no linear pattern, but we can see the effect of the 19,000 cutoff, right? Like the missing triangle on the top right.
Yeah.
Is the $19,000.
So, right. So finally, we did now the.
So I have a question. So would we call this a good model if at all it's having this kind of which I might take as under estimation for some prices?
Yeah, that's what I was thinking. So I think probably we can clearly say it's a good model.
Yeah.
So that like, you know, log carrot equals 0. I don't know, 2, 3. But maybe not beyond that. I don't know.
That can be fine. Okay.
Yeah. So finally, to even confirm that our works is our model is okay, we can plot this box float we used before in our first instance where we used the cut, all this with the price. Yeah, is it the price? Yeah, with the price. But remember, these ones we did it with data, the first data set which have some confounded variable. But now, at last, after doing the residuals, we can do this plot with the residuals, log residuals. So if we do with the residuals, and this will give us the true picture of these patterns in the data. So let's look at the first one where we have the cut and this. So you can see the fare, which is, look at the price. Can you see, this is the cut, this is log, the residuals. Can you see the residual? Look at it here. But if you look at the first case, we have this one. Look at it here. Oh, no. This one, can you see it up?
Yep.
And also when we look at this one, okay, how can we do this? Okay, can we not do that?
There.
Okay, if I look at this one also, look at the bad one, look at the way it is, and the good one, look at the way it goes here. So this is giving us the true picture. And let's look at the final one. Look at the one here, which is the worst in terms of the clarity. And this is the best one in terms of clarity. Look at the residuals here. Can you see it? So this one really gives us the true picture of the pattern in the data, but Hadley makes some statement, I think, from the book here, and I really don't quite understand what that means. Let me show you so that maybe one can interpret that. So you can see, now we see the relationship we expect. Of course, as we can see, this one, the higher quality clarity is here, and also the one.
Shamsuddin?
Yes.
I think you're showing the book.
Am I showing? What am I showing now?
Now you're sharing your studio.
Yeah, so I'm showing the book. I want us to understand. I don't understand this statement. After showing, yeah, I know I'm showing the book. I want us to understand. Someone maybe to explain some part here that I don't understand.
Yeah, but we're seeing the first page of the book rather than the relevant chapter. Maybe you have two browsers open.
Am I showing? What am I showing?
You're showing your PDF viewer.
Oh, right. Okay, let's go on. Okay. I know what I can do. I don't know what happened.
Is it PDF? No, it's Safari. Huh.
It's Safari I'm showing, right?
Yeah. But
Safari?
But you haven't gone to the model building section.
If you click
okay.
the link I just sent.
I'm at the model section now. I don't know what is happening.
Okay.
Yeah.
Welcome.
Okay, let's go. Okay, let's go on. Right. So in the book, Hadley, I don't know what happened. Yeah, right. So if you look at this section immediately after this one, Hadley makes some statement. That is why I say ask someone to explain, which I really don't understand. But let me try to see what is happening. Why so? Not this. Not this. This one.
Yes, you're moving.
I have two more. I have two windows open. Yeah. So, yeah, this part. No, not this part. Here. It doesn't make sense to me. Can someone explain?
So basically, we're looking at the residuals from the model. So our model was the red line that we saw earlier. And a residual, like a positive residual, means that the actual price was higher than what the model predicted. And a negative residual means that the actual price was lower than what the model predicted, right?
Okay.
And and the initial model was fit using log2 transform data. So the residuals are also on that scale.
All right. Okay. So let's go on.
I mean, we could also just plot the actual residues, not the log transformed ones.
Maybe. Yeah, definitely.
Okay.
But like -1. So log of -1.
No,
log of something is negative. Wait.
We can't get the log of negative.
Yeah.
Yeah. Okay, let's continue maybe. Yeah. So now what we have seen is modeling with just one variable. So now let's do modeling with 4 predictors. So the previous case we have seen is modeling with only one predictor, which is price. So let's do that one. And we are going to use the same 3 processes we have seen: visualization, modeling, and residual. So the first one is visualization. So this is the same. This first step of visualization is the same as the first step we have seen with 4 variables. So we can put the price, current price, and all those 4 variables. These are the variables we want to use: current, color, code, clarity. So let's skip this one. So this is the visualization. We can do it by just changing the variable. Which data are we going to use? Okay, after doing visualization, the next thing is modeling. And which data we are going to use. So remember, we have a data set called Diamond 2, which we now already have a residual, something like this. So we're going to use this data, but we're going to use more predictors here. We're going to use four predictors. These are the predictors. We are going to use log transform color, clarity. So we're going to use this one, 4. Now, after what we need to do for modeling is just fitting the model. So let's fit the model. This is the first step, as we have seen. The second one is to create the data grid. Now, creating the data grid here.
Shamsuddeen?
Yes.
So sorry, could you do a summary of this model? Yes, the summary of that model, just to see the signs of the parameters.
This one, right?
Yes.
Okay, summary.
Yes, summary of that. I think even that should be able to produce the coefficients.
What do you want to the coefficient of? Okay, this is a summary.
Yeah, we can keep it there. It's okay.
Okay. Right. So what do you want to talk here?
No. So I wanted to see the signs so that when we go into the plots,
okay.
we kind of see what's really happening easily.
Right. So the first thing for modeling, as I said, is to fit the model. So now we fit the model with 4 predictors here, and this is the data, the data set we have been using, which is Diamond 2, not the original data. Now, then creating the grid. Now, for creating the grid, as usual, what we do, this is the data grid, and we put here our variable that we want to work on. This is a predictor variable, and we do the add prediction with the model we do, and we can see that. But I'm not sure why here. What the book does is that while creating the data grid here, they add this variable, this dot model. So if we remove this dot model and we try to run this, we can get an error. So what really happening is that this data grid, it must have, after you put this first variable here, data, you must have another thing. So what Hadley, as I look at it here, is that, let me see the second one. Let me show you something. Right, yeah. So if we look at this one here, from the data grid function, this is the data grid function. Am I showing my screen?
Yes.
Okay, so this is the data grid from model R, and this is data grid. So from the data grid here, the function, you can see that after you put the data, model equals to null. So if this is missing whatsoever here, and also model is missing, then abort report an error. Must supply at least one of these or model. So if you look at it previously, what we have been doing, when we add a grid here, add grid, can you see that add grid? We put the data grid, yeah, data grid. We put the data here, right? Data grid, but here we didn't put anything, the second value.
So but basically, I'm thinking if you go back to the code that gave an error, I think it would work if you assign the cuts to something, wouldn't it?
So what he said, if you supply
for example, if you
model,
say like I don't know, like x1 is equal to cut. I don't know. I've never seen this error before, actually.
Yeah.
But if you say from the grid, if you say, for example, cut 2 is equal to cut.
Something like this, cut 2 equals to cut.
Yeah.
Okay. So let's see.
But then that shouldn't work.
With a U, you wrote A.
Yeah. Yeah, but then the model wouldn't understand it. Really weird.
Yeah. So what he says is that if you supply a dot model, missing predictors will be filled in with typical values. I really don't understand what he means by the missing in predictors will be filled in with missing values. So this is the section of the code I highlighted here. So now when we add this one dot model and we put the model, we feed it. So look at the model we feed it.
Okay, I get it. I get it.
Yeah,
so
this is the model we fitted, right? So when we fit it here, you can see that we have this, the code, this, and this L log, the log transform caret is the typical values. So what is the meaning of typical values here? They calculated the median. So when we calculate the median here, look at this from the data, we select this variable and we find the median. This is this. So they fill in this one here with the median value. So I don't understand why do we need this, Alan?
Yeah. So basically, if you just put up like a code chunk before that, and you only do I don't know how to call this, data grid without adding the predictions.
I remove this.
Yes, but you can put it in a new one. So you just remove that, but then remove the model thing inside the data grid. Then that should be able to work.
Okay. So I remove this one, right?
Yes, remove that. Then remove, of course, the.
So you are saying this one will work, right?
Yes.
Okay. So what does that mean?
Have you run it?
No. Okay. Yeah.
So the thing is that this is a categorical variable, and the model references uses one of the categorical variables as a reference. So in this case, that specific variable or that specific level of the categorical variable will not be understood by the model. So it will be like a new data it has not seen before. Then it's going to be replaced with some kind of like zeros or whatever, nulls, whatever it does. So basically, we need to communicate to the model that this is the data set that we are using in the model, and whatever you use as a reference, please also tell our data grid that it is the reference. I don't know whether it makes sense.
Okay.
So if in the same function now you also add comma dot model equals mod diamond 2, then we can see the output of that.
Okay.
But Harvard, did you mean before you add the predictions, right?
Yeah. Just direct comparison.
Yeah, that would be good to see.
What do you say, Harvard?
So if you just highlight diamonds 2 pipe data grid and then just run that bit.
I highlight diamond 2.
Okay, if you comment out add predictions and comment out the final pipe so it doesn't complain.
Right.
Yeah. And run that now.
It doesn't complain.
I don't know. I don't see the result.
Yeah. Me too.
Could you just press the play button there? Where is it? Where is it? Oh God. Oh yeah, this one is not updating. Interesting. Oh, okay.
But look at the color. Who gives color? Okay. We have color. Okay, GG. Yeah. But there is no okay, we didn't add the prediction.
Yeah, true.
Oh yeah, I mean, this is still the same thing, but we didn't add the prediction. It's quite the same thing. There is no difference, right? What about this one? Can we do?
No. There is a difference.
What is the difference?
The difference here, and I hope I get it right.
There is no difference.
Yeah, I think the difference is that if you actually look at, there's no difference. Oh,
No, you just remove one layer. You just remove one layer. So if we went to do that, if we want to do what Hava was saying, maybe to see something is just from this step where it doesn't work, where we didn't add this model at diamond 2. Can you see that? So when we run this, as we see, it worked before. So yeah, so this one. Also, in the previous way, I can see that we have only data. We didn't provide this, something like this. Ah, okay, right. Maybe let's see this. Let's look at this one. So what they are saying here, if we look at the function here, this is the data grid, right? So if we have the data grid, it has 3 arguments. The first one is the data. The second one is the range you give for the variable, and this one, the third one. So there must be at least one of these, either this or this, either this or this. So if you look at the previous one here, we have this, which is the data, what we want to use, and we have this. So let me look at, I'm quite cool. Let me look at the add grid, the previous one we used. Data grid.
Yeah, but Shamsuddin, I think the statement in the book is not related to you adding the variables or the arguments in the function that are grid. It's more of trying to communicate to the model that this is a categorical variable and you need to actually be aware of it and you need to put in figures for it.
Okay.
So it's not about the error, really. That's why before, when we added only cut, it works without adding the prediction. But when we want to add the prediction, then we need to add the dot model argument also.
Right. So let's make progress. So that is that. So we see if we plot this with the grid and with the cut and prediction, you can see here. And finally, after fitting the model, then plotting the residuals in the same way, you can see the pattern here is not that good, and we can say that our model is good because this pattern is not quite any way we can see whether it is linear. So this is the first exercise. The first one is said in the plot of the days L log correct and log right, there are some bright vertical strips. What do they represent? So here we have some strips here. So what do they represent here? I'm suggesting because maybe we have many diamonds at this place. So that is why it's somehow bright. I don't know. This is the,
and I think it probably represents like round numbers, I would say.
Round numbers. What do I mean by round numbers?
Like 1.5 instead of 1.23789. Like
okay.
Maybe. I don't know.
Okay, right, I got you. But okay, here we have that one. Here also we have that one, and here we have that. All right, okay. We have number 2.431. I didn't attempt it. I think maybe we can come back to it. And we have this one. I'm looking at the time. So extract the diamonds that have very high and very low residuals. Is there anything unusual about these diamonds? Are they particularly bad or good, or do they think these are pricing errors? So basically, the question is asking us to extract diamonds that have high and low, very low residuals. And we think about this diamond, whether they are good or bad, what their price. So this is the data, diamond 2, and we add residuals as usual, and we create a column, log transform residuals. And here we're trying to create a quantile where we have the first 25% at the very lowest, maybe residual, and the highest percentiles, the one with the highest percentage, I mean, very high. So using this one, we can plot and see if there are any patterns. So after we do that, we can see our filtered variable here. We plug it here at the data, and this is the cost, this is the price, and we see, yeah, I mean, there isn't any striking information here. This is fair, and you can see its price is the one which is lower than the other ones. Yeah, probably. And also this is the price based on the color. So we know that this is the highest price, and you can see the price is higher. I mean, this is the good color and this is the worst color, right? And we can see here the price is somehow. And finally, based on clarity, this one is the worst with the clarity, right? And we can see the its price is not that high because it's not clear diamond, but this one is clear diamond. But what about this one? This is the diamond with clear, and if a diamond is so clear, I think it does have it is somehow expensive, right? But we have some kind of the price here is relative. Look at the price. Does this really make any pointer? I'm not sure. Do you understand what I mean?
Yeah. So here, I mean, I don't think that gives us much information, but for me, what I'm seeing is a lot of outliers still in the data, based on the box plots. You know, like those dots that you're looking at. The dot.
Yeah, but here we don't have outliers here.
Actually, I think the box plots suggest different.
Yeah, but when we have the outlier, I mean, we expect to have, I don't know. I mean, this one are not outlier, right? It's just telling us the where we have the price is higher than the lower. They are not telling us here as outliers, right?
No, those are outliers.
So we plot this. These are outliers?
Yes.
You sure?
Yeah.
Alan?
Yes.
Okay.
Because so
okay, now look at it, Alan. Okay, so now here, if you say these are outliers, we don't have any value here. We don't have any value at the median or at somewhere. We don't have any value here. We don't have any point here. The whole data set, we don't have any point at the medium or at the first, even lower quartile. All the values are upper. So
no, that's not what it means. The value, the black line you see in the middle, that's your median.
Yeah.
And inside the box, you have your interquartile range, but that doesn't mean like, yeah, those individual dots, like beyond basically the line, they are your outliers.
So all these values are outliers now here?
Yes.
Yeah, but those aren't the only values you have in your data set.
Yeah.
So maybe I misunderstood. So what is the first, I mean, are these also all outliers?
Yes.
Right.
So basically, if you just ignore the outliers, then interpreting and trying to see the patterns in the prices, you can just eyeball the medians for each of the box plots.
Okay. So my question here is, where is the original? Okay, I do expect to see some points along maybe the medium price or in somewhere in the inside the box plot to tell us some prices. But why don't we have some points which represent the clarity somehow close to the median or close to the lower Why don't we have that? Hello, Alan.
Yes, hello. Sorry, I missed you a bit.
Yeah, yeah, okay. Yeah, so this means that this data set is whole outlier.
No, not really. I can't really answer that with certainty, because you need to know, for example, in every category, how many of those are considered outliers by the box plot, and you know that.
Right, I understand what you mean, like the extreme values are outliers, right? So I expect that outliers somehow are points that are far from normal in the box plots. So this point, they are not far, it seems to be they are normal, but they are having higher prices, because assume that maybe this price, all this one, they have continuous, maybe they are somewhere here, but we have only one here or two at the top, which is far from the normal, then we can say those are outliers. But all these prices are continuous, they are within the same range. So I'm a bit confused. Yeah, I think we are running out of time. We are having 7 minutes. So we continue, I think, from the second part, right?
Yeah, so because like if you want, we can discuss more about this one here later on.
Yeah. So yeah, maybe
but I think
don't...
like what Harvard's posted in the chat is a very good starting point.
Good, Harvard. Yeah, thank you, Harvard. This is really his.
No problem. Yeah.
Yeah.
If you like the basically position of the box and the whiskers, which are the lines going to the top and to the bottom, are defined in the box plot documentation. You can look. It's basically 1.5 times roughly the interquartile range. So anything beyond that is considered an outlier.
Yeah.
We can discuss it.
Yeah. Okay.
Session.
Yeah.
Right.
So it means that the best way to remove outliers for this data set or this plot would be to do the interquartile range for each of the categories. Then that way we know that most likely we have removed the 20. We're only considering the 25 to 75% of each of the category.
Okay. Right. Okay. Good. Yeah. Good discussion. So I actually miss. I think we can stop the recording. Yeah.
Yeah. Let me do that.
Right. Yeah. All right. So welcome back to R4 Data Science Model Building chapter. In the previous week, we have seen, we have went through the content of the chapter, and we started doing some exercises, but we haven't finished. So today we will go through the exercises of the chapter. So basically, we will see 2 sections of the exercises, with the one we have started seeing, which is this one, 2.43, and also the last exercise is this one. So let's start going and see what we can do. All right. Yeah, I think for the first one here, we have seen what this is, which is a in the plot of this and this, there are some bright vertical strips. What do they represent? I think we have answered this one, where we say they actually represent maybe that they are, okay, we said that in digit like 1.5, 1, and 0.5, there are more diamonds in those regions. That is why we have this sharp stuff. We have seen that one this week. And about this one, we have not discussed this one, where I said that I didn't understand the question last week. So let's go through it. So the question says, if we have this, what does that says about the relationship between the price and the current? So obviously we know that this relationship is a linear relationship. So this is what I think, that the price of the diamond is completely dependent on the current side, but only when the relationship is linear fashion. So this is telling us there is a linear relationship between the price and the current, which is the size. And also, as you can see, a 1% increase in current is associated with a 1% increase in price. So this is basically what this relationship is. So 1% increase in current is associated with 1% increase in price. Anyone with another input? So basically what I thought, this is how we represent linear relationship. So this is telling us in a linear relationship, we are looking about change of increment if one will affect another one. So in this case, we have 1% increase associated with each one. So any input from anyone?
Yeah, so I'm thinking that the relationship is really between the logarithms of the two variables, the logarithm between price and carat. Otherwise, we can't really say much about the linearity.
Yeah, so
the logarithm.
Yeah, so I think what we are talking about here is all this relationship, and this when we plot this, what kind of relationship will we see when we plot this one? So what we will see definitely, as we have seen previously, is a linear relationship where this log and this log tries to change this relationship to be more linear. Before, if you remember, where we see without taking the log of each of these ones, and the relationship wasn't that very much linear. But when we took the log of each one, the relationship become more pronounced that it was linear. So that is why I think it is. They are not only asking us is that log that makes this relationship linear or not. They were asking, what is just the relationship between the price and current? So if in terms of this relationship, I think it is linear. Yes, Alan, can we move on? Or there's something?
Yeah, but anyway, what I can say about the second one, then it's more of like we can say that the 1% increase in the carat is associated with a 1% increase in price.
Yeah, that's right. Yeah, that's right. This because this is the increase. Yeah, something like this. So A1, I just because this is A0 and yeah, something like that. All right. So let's the other one. So this one we have seen it where we said we extracted the diamond and we see there also a strong outlier. So let's go to the last one, which one we have not seen. The final model, this do a good job of predicting diamond price. Will you trust it to tell you how much you spend if you were buying the diamond? So does the final model, mod 2, do a good job of predicting diamond price? So this question is basically asking us how the model is. Does the model have a good performance? So let's look at this. Try to plot the residual. And as we have seen, when we have a model and we try to plot the residual, and when we don't have some kind of pattern or linearity, we can say that the model is somehow doing good because the residual is expected to be somehow doesn't have pattern. So from here we can infer that our models is making some sense, but also we can actually use how can we model, how can we check model performance? So for us to check model performance, we use some measures like R square, RMC, MAE. So I was thinking in this way, we can use these measures to measure the performance of the model. So this is the model and this is the data, right? So final model. So this is the model and this. So when we run this to find these parameters, we can see what that the model is making good prediction or not. So we can see the R square, root mean square, and MAE. So we can see the R squared, the higher the R squared, the better. So we can see we have something like this, and also, but root mean square, the lower the RMSE, the better we can see. So I don't know what we can say. So does it model based on this parameter? Is that making good prediction or not? What can we say? Allah, good? So what can we infer now? If this making?
I mean, really, I find this I find it hard to talk about models, whether they are good or not. But I mean, if you're talking about a square, a root mean square error, or mean absolute error of about 20% or 40%, it's still fine. I mean,
okay.
I've seen people in big organizations presenting models with about 60% error.
Wow. So this is a good model in that case, right?
Yeah, pretty much.
Okay. Right. So this is what the question is asking us. Does the final model do a good job of predicting diamond price? Will you trust it to tell you how much you spend in your buy? So, Alan, it means you will trust this model.
I mean, if that's all I have, yeah, sure thing.
Right. Okay. So so these are functions from functions from model R. They are used to calculate the stuff, and we can also use the summary stuff to obtain some of these parameters. So when we run this, you can see we can have this R squared, which is this, which we already obtained here. And yeah, so adjusted R squared. So what is this adjusted R squared? I don't know this. What is this, Alan, adjusted R squared? Is it R squared or what?
No, it is R squared, but I've forgotten what's adjusted for specifically.
All right. Okay. So what I'm saying here is that you can calculate these parameters model performance with this function from model R, these functions, or we can also see them directly from this summary function, which is base R function. So you can see residual standard error, which is this, is something like this, right? So we can see them from there. So that is, I think, the answers from this question. So anything else someone can add? Anyone, anything else? Have Ruth, Alan?
No.
Right. Okay. So in that case, we can move on to the next, the last part of the exercise, which is exercise 104.3.5, and we see. So here we have so many exercises. So let's see the first one. So the first one says use Google. How can we say this?
I think Hava and Ruth can help with that.
Sleuthing.
Sleuthing.
Sleuthing, yeah. Like detective skills.
Sleuthing.
Yeah.
Oh, in other word in English, what do you call it in another word?
I would say detective. If
Right.
someone's a sleuth, they're a detective, yeah.
Like
Right.
slithering.
Pardon?
like Slytherin in Harry Potter?
No, but that's a funny link.
So sleuthing means detective skills, right? Or
Basically, yeah.
Okay, yeah. Thank you for the English. So use your skills and reason why there are fewer than expected flights on this day, January 20, May 20, right? Okay, 26 and September 1. So let's see what these are. These days were Saturdays. So if we look this, so this graph is obviously we just select the Saturday here, and we can see here January 20, right? January 20, we can see we have sharp, right? And we have May 26, right? May 26, and we have the last one, September 1. All right, September. So the question is basically, okay, why there was fewer flight on those days. So I didn't use goals anyway. Here's what is said. All these days are holidays in the US. So what the meaning of this is that 21, so all these days, 21 is, I mean, if you, the first one is 20, right? January 20. So it means the second day is 21. So people were going to, already going to their, for holidays, and 26, and we have September, oh, September 20, what? September 1, right? September 1, okay. So these are these days. So that is why there are fewer flights. So you see, that's the reason. So how would they generalize to another year? They might end up in another day of the week. So this is the question they ask. How will these days generalize to another year? So if we look at this one here, January 20, we have sharp 4, but this means this is a day to holiday in US. So maybe nobody take a flight to go to work or for travel business purpose, because the next day is holiday. So yeah, and May 26 and September 1. So let's see. They ask how can we generalize? So let's see what will happen these days in the next year calendar, maybe 2014, 2015, what will happen, in which date they will fall. Picking up these days, 21st, this one, 26, and this is 02, right? So when you look at it here, the days they give us, January 20, so it means the next day is holiday in US. May 26th, that is Trinity Sunday, and September 1, the next, that is September 2nd, is a holiday. So it means those days, they are, what do you call it, a day to a holidays. That is why there wasn't much flight. So we pick up these days, 21, 26, 02, those holidays days, and see will they fall on these days. That is why will they generalize to have the same date as in 2013? Yes, of course, we know they may not. So we can see in 2013, they are Monday, Sunday, and Monday. These days, 21 is Monday, 26 is Sunday, and 2nd September is Monday. So in subsequent year, which is 2014, these days, 21st It's Tuesday. So they don't actually generalize to the same day in other years. So that is what this means. The question, how will these days generalize to another year? So they will just fall into another day, which is obviously something obvious. So any question?
No.
Right. So so this is this one. So let's go to the next one. So what do the 3 days with high positive residuals represent? How will these days generalize to another year? So so this is asking us 3 days with high positive residuals. So 3 days with high positive residuals. So this is our daily, and we can take the top 3 residuals this way. And as we can see here, as expected, these are Saturdays, Sundays, and they have high residuals. It means they have high error, right? I mean, so the top 3 days correspond to the Saturday after Thanksgiving days, which are these, the Sunday after also Thanksgiving days, and the Saturday after Christmas, December days. So we have high residuals. It is telling us that the model underpredict the number of flights. So the model doesn't perform well on these days, because if the model performs well, we will not have such kind of high residuals. So what do the 3 days with high positive residuals represent? So these days represent these days. And how would these days generalize to another year? Right. How would this day generalize to another year? I don't know. Yeah. So, I mean, the question asks the first thing, what do they represent? So these days are Saturday and Sundays, and they represent these days. And what it is really meaning that why we have high residuals in that the model underpredicts these days and it doesn't perform well. So I don't know the second part. Someone can help us?
I don't know if I interpreted it right, but I took it that we know when Thanksgiving falls and when Christmas falls, so we could sort of build them into the model.
Sorry?
So to generalize it to other years, you could sort of mark those dates, couldn't you? You could say, okay, so Thanksgiving's the 4th Thursday of November, so we know what the Saturday after that would be, and then you could build it into the model so that it would account for it in future years.
Okay. So the same as the previous one, something like that, right?
Yeah, that's what I thought.
Yeah, okay. Yeah, all right. Okay.
Yeah, I think that makes sense, because since they're variable in terms of like the like which particular day they fall on, you need to add them separately.
Right, okay.
Yeah. Because what I was thinking about also was that if you look at Christmas, for example, people don't really travel on Christmas, but the days before Christmas and after Christmas, there is high volumes of people. So the model is going to kind of like try to predict Christmas based on the number of the data points around it. So that means that we're not going to get Christmas to be accurately predicted as we would have wanted.
Okay, yeah.
So it's highly possible that Christmas is going to be over-predicted or even under-predicted, but I'll guess over-predicted in this case.
Okay, right, okay. All right. So let's go to the next one. So this one says, create a new variable that split the day variable into terms, but only for Saturdays. That is, it should have Thursday, Friday, but Saturday summer, Saturday spring, Saturday fall. How does this model compare with the model with every combination of the working day and time? So this is asking us to compare two models, The first model is the one we use with the working days or weekdays, the normal one we have used in the chapter, and we create another model with what we call term, and the term will have inclusion of something Saturday summer, Saturday spring. So let's look at the first case where we have the weekday. So what is happening here? All right, okay. So if we look at this one here, the first one, we have the weekday, which is the one we have seen before. So this applied, we take a date, and we have this, the normal one, and let's see what this means. So we can see this is the days we have weekdays, and this is the residuals. So let's plot this one and see what happens. So this is the basically the plot for the normal weekday we have. So the question is asking us to create another variable with term like Saturday summer, Saturday. So each Saturday we put it Saturday summer. When we see a Saturday for spring, we put this one. So it's asking us to do another way. So for us to do that, here we do something like this. So here we have this one here where we have the date. Here we have breaks we are talking about, and for those summer and those springs, we have the levels here. We have spring, we have summer, we have fall. And when we create this, so let's look at how this one. So here you can see we have mutate, we have term, so we have this. We have spring now, and we have summer, we have this. And we need to create now the way they want us to do. So let's look at it here. So now here we have term Saturday. So if you look at this one here, we have Saturday in spring, we have Saturday spring, right? When we have, this one is in spring. So when we go to the other one in summer, we'll see that. So the difference between the previous one is that the previous one we used here only the weekdays, but here now we are using the term Saturday, in which each Saturday is appended with spring or summer or stuff like that. And we need to fit the model the same way we do with the previous one. When we fit the models, then we plot it. But remember here, we are using our new daily, because the new daily, and what we do is, this is term Saturday. You can see this is what we are, the predictor, not the previous one, where we have our predictor in the normal way, where we have this, right. So you can see this is the predictor in this one. So now we are using the other way around, and yeah, this one, and we can run it. So so the question is asking us, so look at it, right? And look at this one. Yeah. And so the question asking us, create a new variable that split the weekday variable into terms, but only for Saturdays. That it should have Thursday, Friday, but summer, Saturday, Saturday. How does this model compare with the model with every combination of weekday and term? So from this way, we can see the model, they are more or less the same. I don't know what's the difference. They look more or less the same. Yeah, this is the first one. But when I look at it, they are all the same. So they are pretty much the same. So I don't know. Anyone can put a helping hand whether there's a better answer. Have Alan Booth. Yeah. So then the model, even after creating those way, is still the same, and there is no different pattern. Yeah.
I think like the big sort of drops there probably correspond to public holidays. So basically we have like large negative residuals, which means that the model is under predicting the number of flights. So if it was a regular day, we would expect there to be, I don't know, like between 100 and 200 fewer flights. But those days, there were a larger number of flights. Sorry, yeah, the other way around. Anyway, there were fewer flights on those days. So probably if you wanted to get rid of like the spikes that we see, like the 5 or 6 spikes that we see, you probably also need to include the holidays as well.
Okay, right. So,
yeah.
Like I don't have the data for those sort of actual dates.
Shamsuddin?
Yes.
I'm thinking that we're also supposed to do another model which takes into consideration the interaction between the weekday and the I don't know, the season. Then we'll have 3 models to compare with.
Okay, I see. Okay.
I'm just hoping that that one will be much better because it will capture all the variations throughout the days and the seasons.
Okay, right. So yeah, for this one, I think there's not any difference between the two. They're more or less the same. Yeah. So let's go to the next one. Okay. So the next question says, create a new weekday variable that combines the day of the week, time, and public holidays. So this is telling us to create a new variable that combines the day of the week, the time we created before, which is Saturday, spring Saturday, and public holidays. So now we have public holidays in addition. So what we were saying before. So what do the result of the model looks like? So this is it. So if you look at this one, this is the new daily, which the one we created the term, and now we want to check if these are the holidays days. If the date falls in this, then it says it's holiday, else nothing. And and we use the function unite so that we can create a new variable called new term and unite the term Saturday and the holiday column. So if you remember here, this is what we mean. So if you look, previously we have this term, right, which is spring, right? So if you remember, previously we have term Saturday column. In our previous plot, we have term Saturday, and now we created a holiday column. So we unite them into new term. So we have a new term now into Tuesday. If it is holiday, then it attach holiday. If it is Wednesday, if it is not holiday, then it is none. So this is a new data frame now, and we want to see what happened now with new term here. So let's plot it. So I can see that this one, it seems like it reduces, but the one here doesn't seem to change the variation very much, but I can see, for instance, in the previous one, so this one is still there, but the pattern is more or less the same, but it's not that very big. If you remember, I think one of these, the residuals comes even after minus 200. So like, do you expect any pattern here with the previous one?
Interesting.
So yeah, so
can you just one quick thing? Can you just try to do a summary of the model 2?
Sure. What is this?
Oh, I see.
Okay, this is summary, Alan.
Okay, yeah, I see. I've seen what I was looking at. Yeah, I mean, I don't think really it's gonna change much actually here, because for me, what I would think is that we might need to consider other variables, definitely, not just the time. And if you're considering the time, then we have to do something like auto regression, so that we take into consideration the previous times for each of the day we are considering. So I highly doubt that this is going to give us any better thing if we're regressing um, the number of flights on the term that we are creating.
Yeah. And we can see here the r squared with 0 0.f something. It's not that. I mean, yeah, but it's not that. All right. So, have a roof any input?
I hadn't got what Alan said. That makes a lot of sense. The only other thing I thought was I think by doing it that way, is it kind of treating all holidays the same, but you would expect to see a difference between like Christmas Day and Veterans Day and all that kind of thing. Like they're not going to have the same impact on travel,
Yeah.
surely, because they're totally different.
Yeah.
Right. Okay. Okay. So let's continue with the next question. So, right. So the next question, so what happens if you fit a day of week effect that varies by month? That is something like this. Why is this not very helpful? So this is just fitting. So this is so oh, it seems it even adds the outliers. Can you see this one? It seems like, yeah. So why is this not helpful? I don't know why the answer. Why? I don't know the answer. So here we put in the day of the week effect, but it's by the month. But still, there is no any improvement over the previous one. But even the outlier given, let's look at this one is coming down, and which is not free. So this is the worst.
I mean, so our problem here, if you look at the spikes, it's not the month really. It goes down to specific days or the holidays that we've been looking at. So the month is not capturing that the fact that the public holidays actually happen on different weekdays. It's not capturing that. It could be the same month, but it's not capturing the specific holiday that we want to deal with.
Yeah, so you can see even the r squared decreases now. We have 0.72, and the previous one we have 0.8. So this one actually decreases even the performance, right? So yeah, the outlier is even more so pronounced in this situation. Yeah, okay. So let's continue with the next question. So the next question says, okay, 5C. So is it maybe I didn't do the next one? Okay. So this one I didn't even attempt it. Let's see the book. So am I sharing the book?
Yeah, we can see it.
Okay. So yeah. Okay. This one I didn't attempt it. So we come back. Maybe let me do the last one. Even this 1.7 I didn't attempt it. So let's see the last one. It is little frustrating that Sunday and Saturdays are on separate ends of the plot. Write a small function to set the levels of the factor so that the week starts on Monday. So this is just creating a function which allow us to makes our data, the arrangement of our data to start, to have Saturday and Sunday in the same. So this is the function. So you can see we have now Saturday and Sunday, then the previous one where we have the Sunday here and Monday. So yeah, so this function called week level. So it basically, given the weeks, it takes have this Sunday and put it after 7. So it will take the Sunday and put it after 7. Yeah, so this is just a basic simple function that rearrange our data. And now we have our plots. We have Saturday and Sunday in the way it is expected. So that is this one. So I haven't attended the 6 and 7. Maybe we have more time, so maybe we can discuss them if they are right. So what this one is saying, number 6, what would you expect the model to look like, knowing what you know about the data? Where would you? So it's basically, the reason why, what is the meaning of this NS? I don't know what the meaning of this NS. So what would you expect the model, this NS, then get 5, knowing what you know about the data, what would you expect it to be not particularly effective? So I don't know what NS is. Ruth, Alan, do you know what NS is?
No, really.
Right, and the number 7 said, why hypothesize that people living on Sundays are more likely to be business travelers who need to be somewhere on Monday? Explore the hypothesis by seeing how it breaks down based on distance and time. If it is true, you expect to see more Sundays even fly to places that are far away. I didn't attempt this one. So anybody attempt this question? Have a Ruth Alan, anybody attempt this question?
Yeah, I don't know if my answer is great, but I think in the end I thought it wasn't a very good hypothesis.
Yeah, so can you share the screen, maybe take us through?
I can't because my code's all old and I've not got it hooked up properly, so it'll all break. I know it will. But I think I just like categorize things by time of day, sort of morning, evening, afternoon. Which was obviously a bit arbitrary, but it didn't really show a difference.
Yeah, I think yeah, so
that's not, I think that's kind of like a weak hypothesis. Because, because I could live on Sunday when I'm, a leisure traveler, in a way.
Okay.
Because we can only make that hypothesis is common if we're talking about weekdays. So normally, if you say people living between Monday and maybe Thursday, they're normally business travelers. However, people traveling on Fridays are more likely going to be leisure travelers. But well, at the same time, it depends anyway on whether people are returning home, for example, or going somewhere else.
Right. Okay. So I think that's the end of the chapter, and so here there are more resources to go and dive deep into the modeling, statistical modeling, a fresh approach, statistical learning, applied predictive modeling. Right. So thank you very much for giving me an opportunity to derive this chapter. And yeah, it has been a good journey. Okay, thank you, Alan. Thank you, Harper.
Thank you too.
Yeah, so we have the next chapter, which is many models. Who is gonna take that? Is that Harper, right? Yeah.
Yeah, can do.
Yeah.